So this video is going to be explaining the deep concept that is pH. Coming up to this point, you remember that acids have a pH less than 7, bases have a pH greater than 7, and water is neutral at 7. But where does all that even come from? So chemically, that's what we're going to be talking about in this video. But before we can understand that, we really need to understand this, which is a little bit hard to wrap our heads around. Water does something that's called autoionizing, or in other words, it breaks itself apart. Now, only a very few water molecules in a sample will do this, but it does happen. And so what happens is, for example, one way to visualize it is H2O breaking apart into H+, right, a proton, and OH-, hydroxide. Another way of looking at it also is that one water molecule will react with another water molecule, two water molecules, and one water molecule will act as the acid, and it will donate its proton to the other water molecule, making the other water molecule a base because it's a proton acceptor, according to our Bronsted-Lowry definition. So if we look over here, the water on the left gave up its H+ and became this conjugate base, right? This water is a proton donor on the left, which means on the right, if we're going from right to left, it's a proton acceptor, it's a conjugate base. This water is accepting a proton on the left, which means on the right, it's a conjugate acid, right? Because if we were to reverse this reaction, this hydronium is what we call H3O+, would be the proton donor if we went backwards. But anyway, the more important part is that one water molecule will react with a second water molecule, and they will become hydronium and hydroxide, respectively. We know that this happens to some extent. So if we look at that, here's our equation again, and from here on out, we're going to be representing it as H+ and OH-. We have an equilibrium constant that occurs with that. So we know that water will reach equilibrium where it's splitting up. Some of it is just H2O liquid, and some of it has ionized into H+ aqueous and OH- aqueous. So we can kind of develop an expression for that. Also, remember that in our equilibrium expressions, we don't include pure liquids. So when we're writing out this expression, we call it Kw. It's the equilibrium constant for water. And we simply say that it's just the products because the reactants are water and that's in liquid form. So we've got a couple of aqueous products. There's no coefficient, so we don't square them or anything. This is just how the expression looks. So it's called the ion product constant, and it's the product of the molar concentrations of H+ and OH- at a particular temperature. So we're going to be, from here on out, using it at 25 degrees Celsius. Remember we said that temperature is the only thing that affects the equilibrium constant? For us, we're always going to use it at 25 degrees Celsius, so we can always assume that it's actually this number. This is the equilibrium constant that's produced because of that. Now, essentially where that comes from, we'll get to in a little bit. But if we look at water, if the H+ concentration, right, bracket stands for molar concentration if you remember, if the H+ concentration is equal to the OH- concentration in the water, you can probably guess whether the solution is acidic, basic, or neutral. If they're equal, it's going to be neutral. However, the moment that there's a higher H+ concentration than there is an OH- concentration in the solution becomes acidic. Conversely, the moment that the OH- concentration is greater than the H+ concentration, all of this is in terms of molarity for us, the solution will be basic. So that's kind of intuitive. The more H+, if you got more H+, they win, it's acidic. If you got more OH-, they win, it's basic. If they're equal, nobody wins, it's neutral. This is kind of representing that as well. Another way of looking at it, essentially. Only, in this case, they're using hydronium instead of H+, but you often see those used interchangeably, because in H+, you can either think of it as just being H+ being produced by water, or you can assume it attached to another water and made hydronium. For all intents and purposes, it ends up doing the same thing. Okay, so what is the concentration of hydroxide ions in a hydrochloric acid solution whose hydrogen ion concentration is 1.3 molar? So we do our setup. We know our Kw is concentration of H plus times concentration of OH minus, and it's equal to 1 times 10 to the negative 24. That's what we established. This number is going to come up a lot. This is different than the other unit. We're going to use this number a lot. So we have the hydrogen ion concentration. We don't have the hydroxide ion concentration. So we can just rearrange essentially to try to solve for the hydroxide ion concentration. So we rearrange to get this. OH minus is equal to Kw over H plus, right? We just divided both sides by H plus to get that. Recommend always doing the algebra first and then plugging the numbers later. And then we plug in the numbers and we get our value essentially. So for a problem like this, where you've got H plus and you're trying to find OH minus or vice versa, simply plug it into this equation, and that's what you can do for that essentially. It's going to get a little more complicated from here. Okay, but again, we're going to be talking about where this pH concept comes from. Remember that the brackets H plus means H plus concentration. So let's take a look at this. When the pH is 0, the H plus concentration is 1. So 1 molar, 1 mole per liter. When the H plus concentration is 0.1 or 0.1 moles per liter, that's when the pH is actually a 1. Now remember, the lower you get on the scale, the more acidic. So as we move up, it's actually less acidic, which makes sense because these numbers are getting less concentrated. For a pH of 2, the H plus concentration is 0.01. And for a pH of 3, it's 0.001. And you could probably guess where this is going. pH of 4, divide by 10 again, divide by 10, divide by 10, divide by 10. So, okay, but what does this even mean? If we look at this another way, let's take these numbers and put them in scientific notation. 1 mole per liter of H plus concentration is the same as 1 times 10 to the 0, right? Because anything times 10 to the 0 is 10 to the 0 is just 1, or anything to the 0 is just 1. So this is like 1 times 1. That's 1. We can rewrite 0.1 as 1 times 10 to the negative 1. And we can rewrite 0.01 as 1 times 10 to the negative 2. And if we keep going with this, now hopefully we can see a pattern. So if you had to like write a rule, how do I get the pH from the H plus concentration? Hopefully at this point you can see that you take the exponent and make it positive. You take the power of 10 and make it positive to get there. So hopefully you realize that that's the connection here. Now, there's an efficient mathematical way to simply grab that power of 10 and change the sign of it. This is the negative logarithm. The logarithm portion is what essentially we're going to be using log base 10. When you apply a logarithm to an H plus concentration, it's going to just take the power of 10 and give you that number. The reason why we have to put a negative in front of it is because all these numbers are really small. So when we take the negative log, for example, let's say I just took the log of 1 times 10 to the negative 2. That would just give me negative 2, which is not a pH, right? So in order to get the real pH, we then take the negative of that, which is just a 2. So that's what we're looking at here. pH equals negative log of H plus. From here on out, you want to think of P as meaning negative log. P means negative log. In this case, we're doing the pH, so it's the negative log of the H plus concentration. That's how we find this. So if the solution is neutral, those are equal, and H plus is 1 times 10 to the negative 7. Now, where does that come from? Well, both of those numbers, let me just show you this. pH is 7. Remember that our numbers were H plus times OH minus equals 1 times 10 to the negative 14. When you multiply exponents, you add their powers. So if it's H plus times OH minus is 1 times 10 to the negative 14, that means that the H plus has to be 1 times 10 to the negative 7, and the OH minus is also 1 times 10 to the negative 7, in order for those to both add up to 1 times 10 to the negative 14. Another way of looking at this too, which we'll get to, is that if you take the negative log of 1 times 10 to the negative 7, you get a pH of 7. And that's because these two are equal at the moment, which is neutral, right? If it's acidic, that means there's more H plus concentration. which means the H plus is greater than 1 times 10 to the negative 7, which means the pH is less than 7. They do the opposites pretty much. The greater the H plus there is, the lower the pH is. Okay, for something to be basic, that means the OH minus is winning, right? So H plus is less than OH minus. That means the H plus is less than 1 times 10 to the negative 7, which means that the pH is greater than 7. The more concentrated the H plus is, the lower the pH is. So the higher the concentration, the lower the pH, right? The more acidic. And the opposite is also true. The less concentrated H plus you have, the greater the pH is. Another huge thing is that the scale is logarithmic, which we just saw a second ago. So that means a pH 1 has 1,000 times the H plus concentration as a solution of a pH 4. Also unitless. There's no unit for this. Good news, right? But yeah, every jump you make is a 10 times multiplier. So going from pH of 5 to 4 is 10 times. 5 to 3 is 100 times. Going from 4 to 1 is 1,000 times because it's 10 to get to 3, 10 to get to 2, 10 to get to 1. And you multiply them, you don't add them. So it's 10 times 10 times 10 for every step that you make. It's a huge difference in this logarithmic scale. So when the pH goes up, H plus goes down and vice versa. Okay, so let's do some kind of examples here. Let's go the other way. If you're trying to figure out the H plus concentration and you're given the pH, right, H and H there, you simply take the pH value and make it the negative power of 10. So if the pH is 4, then the H plus is 1 times 10 to the negative 4. Now, most cases will not work out this perfectly. You're going to be using a calculator a lot for this, but you want to know the scale. So all we did was we made 4 a power of 10, and we made it negative. If the pH is 11, to get the H plus concentration, we make that 10 to the pH and make it negative. So the formula is 10 to the negative pH, essentially. So hopefully you'd be able to guess that this is 1 times 10 to the negative 11. Notice the molar here because this is a unit. These are concentrations in molarity. pH doesn't have any units, but molar concentrations do. Okay, let's go backwards now. If the H plus is 1 times 10 to the negative 7, then the pH is, right, so you just take the negative log. So in other words, you grab the power of 10, make it positive, 7. Take the negative log of this. Negative log of 1 times 10 to the negative 3 is just 3. Now, like I said, in most cases, we're going to give you real numbers. These are sort of perfect world, unrealistic numbers just to get the idea down. But you're going to be using the calculator. The most important thing is just focusing on the scale. To get from here to here, make this a power of 10 and make it negative. To get from here to there, take the negative logarithm of this, or in other words, the power of 10, and make it negative, so make it positive, essentially. So let's take a look at the pOH now, which is a lot different, but similar. So remember we said that pH was the negative log of if you have H. P, we said, stands for negative log. So the pOH is the negative log of if you have OH minus. Follow the same pattern, right? So if the OH minus is 10 to the negative 14, that means the pOH is 14. We just grab that power of 10, make it positive. Vice versa, if we have a pOH of 4, that means the OH minus is 10 to the negative 4. We take that pOH, make it a power of 10. So let's go backwards then. If the pOH is 4, what's the OH minus concentration? 1 times 10 to the negative 4. Now we're only allowed to do this because we have OH and OH, right? If the pOH is 11, the OH minus concentration is 1 times 10 to the negative 11. Okay, now let's go the other way. If the OH minus concentration, this should have units, is 1 times 10 to the negative 7, then the pOH is just 7. We take the negative logarithm. If the OH minus concentration is 1 times 10 to the negative 3, the pOH is just 3. So hopefully we're seeing the pattern here, but again, it has to be the same things. Otherwise, we've got to change it up a little bit. Okay, now let's see how this all relates to each other. pOH also relates to pH if you haven't made that connection yet. The two of them sum or add up to 14. So if the POH is 14, the pH is going to be 0. If the pH is 4, the POH will be 10. Now this makes sense too because we said these other exponents have to add up to 10 to the negative 14. So if the H plus is 10 to the negative 4, that means that the OH minus is 10 to the negative 10 because they have to multiply to add the exponents to be 10 to the negative 14. We take the negative log of this guy. That gives us our pH, which is 4 because we took the negative log of H. Take the negative log of OH. That gives you POH. So these are all interrelated. And this is just showing they both add up to 14. Here's the pH scale on bottom. Here's the POH scale on top. They're exact opposites. They run in opposite directions, but they both add up to 14 is the simplest way to think about it. And you could do 14 minus 1 to get the other, 14 minus the other to get the other. Okay, so formulas we've established. The H plus times the OH minus concentration is 10 to the negative 14. So those things, the exponents need to add up to negative 14. Because when you multiply things, the exponents add up. pH and POH add up to 14. So we can combine these. So we looked at these other examples before. Here's our combination of formulas we started to learn. But think about this one. If H plus concentration is 10 to the negative 2, then OH minus concentration must be 10 to the negative 12 because they have to add up to 10 to the negative 14. Okay, these are our formulas. You'll be given these, I believe, but this is just essentially the shortcuts of how you get there. To find the pH, do the negative log of H. Find the POH, do the negative log of OH. To go from H plus to pH, to go from pH to H plus, 10 to the negative and then make the pH the power. To go from concentration to go from POH to OH minus concentration, 10 to the negative and make the POH the power. And then these two sum to 14. These multiply to get you 1 times 10 to the negative 14. Here's just those formulas again. But okay, so here's what we're gonna finish with this part. The whole idea with this is if you have any information at all about this, then you can solve for the rest of it. You just need one of the 4 things and you can find the rest of this, or in this case, 5 things for this table. Our H plus concentration is 1 times 10 to the negative 6. So what can we get from that? Well, if we do the negative log, we get that that's pH of 6, right? H and H are related. Okay. Another way we can think of it is we know pH and POH sum to 14. So that means that's going to be 8. And if that's 8, then the OH minus concentration is 1 times 10 to the negative 8 because we can compare OH and OH directly. Now, would this solution be acidic, basic, or neutral? Let's go back to basics. No pun intended. The pH is less than 7, so that's going to be acidic. All right. If something's neutral, you know that that has a pH of 7, which means POH is also 7 because they add up to 14, which means the OH minus concentration is 1 times 10 to the negative 7 because this was 7. And because the pH is 7, that means the H plus concentration is 1 times 10 to the negative 7. Hopefully this is starting to connect. All right, if we've got our OH minus of 1 times 10 to the negative 4, that can tell us that the H plus is 1 times 10 to the negative 10, right? These powers have to add up to 14. Also can tell us that the pH is 10, because the negative log of this is 10. And the POH, 10 plus what is 14? 4. And again, the solution would be, look at the pH, greater than 7, basic. All right, now we're going to start with the POH. POH is 3. The easiest thing to do is say, okay, well then the pH is 11, adds up to 14. And if the pH is 11, that means our H plus is 1 times 10 to the negative 11. And our OH minus is 1 times 10 to the negative 3. And the solution is basic because of that high pH value. And last but not least, if our pH is 9, our POH is 5, which means you can go any direction from this. Our OH minus concentration is 1 times 10 to the negative 5. Again, this is all in moles per liter. And then our H plus is 1 times 10 to the negative 10 because of our pH. And the solution based on the pH is basic. So you need to be able to quickly go from one of these to all of the rest. and you need to get the timing down so that you can focus on tougher problems, because this is going to be one of the less challenging aspects.